Alrighty, guys, this is module 11. Let's get into it. So, basically, early on in the study of the human brain, we didn't have a lot of tools to use. One of the only tools that we had to use were case studies, like in the example of Phineas Gage. Another tool that we had kind of earlier on in our scientific method of studying the brain were lesions. So a lesion is basically a natural or experimentally caused destruction of brain tissue. Now, in today's psychology world, researchers might purposefully cause lesions in animals such as rats. So they will, let's say, damage the lateral hypothalamus, and then they will be able to see what behaviors are altered based on that destruction. Another method that they can do is stimulate brain areas. So in the opposite of lesioning, we can just stimulate a brain area by placing an electrode in there. And what we have found is that different things happen when you stimulate different brain areas. So for example, with an amygdala, if you stimulate it in a human, it will produce a type of an emotional response. So we know that the amygdala is responsible for emotion. Today we have much more advanced technology, so we're going to talk about that in the next slide. So we have got a bunch of different types of scans. First, we have the EEG. Basically, what this does is it measures the amount of electrical activity in your brain. It cannot tell you where that activity is happening, just the overall brain waves. These are often used in sleep studies to look at the different types of brain activity at different stages of sleep. Then we have the MEG. This basically does the same thing, except by instead of using electricity to measure it, it uses magnets. CT scans are basically X-ray photographs of the brain, and these are good to help reveal brain damage. We have PET scans, which show the brain's activity by showing brain areas' consumption of glucose. It can also show hotspot areas of activity during different tasks. They have found, like, for example, when studying the brains of people with PTSD, that their brains use glucose differently in certain areas than people without PTSD. So it can help us show interesting things like that. MRIs help us to see the brain anatomy, and they use magnetic fields and radio frequencies to basically produce these computer-generated images. And then fMRIs combine that feature with the ability to basically compare image after image of the MRIs when a person is doing a given task, for example. So let's say, for example, I am talking right now and they're doing an fMRI of my brain. They would be able to see where the blood is flowing to in the brain, because that's the area that's being used. And that would indicate that that brain area, in this case, probably my frontal lobe, my left frontal lobe, which is important for speech production, would be lighting up. So fMRIs are really cool. This is like cutting edge research that they're doing today. Okay, now we have a bunch of different brain structures. We're going to start from the bottom and work our way up. So at the bottom of the brain is what we call the brainstem. That is this portion right here that is made up of the pons and the medulla. And this serves as the crossover point, meaning that so the right side of our bodies are actually controlled by our left side of our brain and vice versa. So this is where that crossover point happens. Now, the two structures that make up the brainstem are the medulla and the pons. The medulla, this basically controls our heart rate and our breathing. This is why a person could be in a coma but still be like alive, is due to the medulla. Then our pons sits above the medulla, and this handles the coordination of movements and sleep. So the pons is going to work together with the cerebellum to coordinate movement. Then the thalamus sits above these two things, and the thalamus basically works as the sensory board director. So what I mean by that is, for example, my brain right now is receiving auditory input, visual input, and when that sensory information is going to the brain, before it can go to its specific area to be processed, it's first going to go to the thalamus, which is going to be like, oh, okay, this is auditory input. I'm going to switch this board. I'm going to send that information now to the temporal lobe. Oh, this is visual input. I'm going to send that to occipital lobe. So it's basically the director of sensory input. Okay, now if you go back, if we see right here, this structure inside, this is what we call the reticular formation. And the reticular formation basically is a neural network that forms kind of like a net. And what it does is it allows us to multitask. So if you've been multitasking at all today, it's due to your reticular formation. It's also responsible for arousal. So it kind of helps us to wake up or fall asleep. So for example, they destroyed certain parts of it in a rat, and they found that when they destroyed the reticular formation, it led to a coma. When they stimulated this region in the rat, it made them extremely awake and alert. So if you're tired, maybe you could blame your reticular formation. Now, the cerebellum is this little guy, this little guy right here. And we call him the cerebellum because it is the little brain, because it kind of looks like another little brain under it. And the cerebellum does a lot of stuff, but some things that it does is it controls nonverbal learning, skill memory, time judgment, and emotional regulation. But a big role that it plays, the main thing that I want you to remember that the cerebellum does, is that it coordinates voluntary movement. So if I'm waving my hand, this is a voluntary movement. If I'm kicking a soccer ball, that's a voluntary movement. If I'm walking, that's a voluntary movement. The cerebellum coordinates all of those. Now, when a person drinks alcohol, often they stumble because their cerebellum is being affected, and so their movement is not as easily coordinated. Okay. Then next we have the limbic system. So we're moving from the brainstem right here and the cerebellum, and we're moving up into the midbrain, which we call the limbic system. So the limbic system sits in between the older brain, which we kind of would call the hindbrain, and the forebrain. So it's the midbrain. And it is a neural system that includes several structures, including the amygdala, hypothalamus, and hippocampus. And it is associated with emotions and drives, meaning like motivations. So, first and foremost, our amygdala right here. There are two lima bean size structures in the limbic system called the amygdala. So, pretty much every structure in the brain has a right one and a left one. Same thing for the amygdala. And what they have found is that the amygdala plays a really large role in emotion, but specifically fear and rage. So, for example, they found that in a study on people with math anxiety, so people who were taking a test and they were getting anxiety on the math test, they found that those people actually had hyperactivity in their right amygdala. So, fear and anger, this is being processed in the amygdala. Okay, next we have, so here's our amygdala. Next we have our hypothalamus. And the hypothalamus is right above it's actually below the thalamus. Pardon me. Okay. So the hypothalamus, mainly its roles are the 4 F's. This is what I want you to remember. Okay. Feeding. So eating and to stop eating, feeding, fight or flight, and fornicating, which means sex. So the 4 F's. The hypothalamus basically helps us to maintain our homeostasis, and it does this by directing the endocrine system via the pituitary gland. Okay, so it has a lot of maintenance activities. It maintains our eating, our drinking, our body temperature. It helps govern the endocrine system, and it is linked to emotion and reward systems. We'll talk more about that later when we talk about drugs. Then we have the hippocampus. And the hippocampus is this region right here. Okay. The hippocampus is very, very important for memory. When we're talking about names, dates, facts, the hippocampus is the region of the brain that does a lot of storage of that type of material. And we call those explicit memories. Now, without the hippocampus, we cannot form any new memories of facts or events. So we know this because there was a patient named HM who had his hippocampus removed. We'll watch a video on it. And basically, it was like 51st dates. He couldn't make any new memories. He basically lived the same day over and over again. Okay. And now I would like you to test yourself, and we'll go over these in class. See ya.